Hello, everyone, and welcome to the first lecture for Analytic Geometry in Calculus 2. In this lecture, we're going to be reviewing the Riemann sum. Now, the Riemann sum is the fundamental concept that underlies all of integral calculus. And in its most basic form, it tells us that to approximate the area underneath the curve of a function, we can do this using a finite number of rectangles. What's more, is that we know that as the number of rectangles tends to infinity, this area that's calculated will tend to the true area underneath the curve. So let's go ahead and get started, see some examples, and see where these types of things come up. So let me begin with an illustration. I want to calculate the area underneath a curve. And that curve, in my case, is going to be given by 1 minus x squared. So this red line represents my curve, 1 minus x squared. And I'm going to calculate the area between 0 and 1. So this region under the curve here, right down here, is the area that I would like to determine. Now, there are a number of different ways that we can calculate or we can create these rectangles. Let's start with a simple idea. And this is the left Riemann sum. And the idea here is that we take the interval, we divide it into a finite number of pieces, all with the same width. For simplicity, let me go with 2 pieces. So I'm going to divide the interval from 0 to 1/2 and 1/2 to 1. This gives me 2 intervals now of exactly the same length, each of length 1/2. And I'm going to produce a rectangle with each of those intervals as the base. And the height is going to be taking the left side of that interval and going all the way up to the function. So left side of the interval, all the way up to the function. And so this is going to give me my first rectangle. Similarly, let's do this for the second rectangle, all the way up to the function. And that gives me the height. And now what I have is I have 2 rectangles here. And each rectangle has area, say, A1 and A2. And the full area that I'm interested in, call that A, is approximately, very roughly, given by the sum of the areas A1 and A2. Okay, then the question is, what is this approximation? What is A1? What is A2? Well, life is pretty good here, right? Because really now I just have to calculate areas of rectangles, something I can do quite well. The first thing that we need to do is we need to calculate what are the heights of these rectangles. So that means that I need to calculate the y value associated to these dots. And the first dot is given by the x coordinate 0. When I plug 0 into the function, I get 1. The second dot is given by the x coordinate 1/2. When I plug 1/2 into the function, I get 3/4. So the height, the y value of each of these rectangles is 1 3/4. So this tells me that my area 1 is length 1, or height, if you will, times the base, or the width, which was 1/2. Similarly, A2 is height 3/4 times the base 1/2. And now a simple algebra problem that gives me 7/8. which is exactly 0.875. Okay, you're probably thinking something right now. You're probably thinking, Jason, that wasn't a very good approximation. And I will certainly agree with you, right? I only used 2 rectangles, so it has its limitations. But what I really want to draw your attention to here is that we definitely overestimated the sum, or the area under the curve. And how do I know that? Well, look at this overhang right here. Right? I'm including lots of area in A1 and A2 that does not actually belong to the full area A. Okay, then let's try a different method. Let's use a right-hand rule instead of a left-hand rule. So let's draw that function again. Oh. Okay, let's start that over. Okay, so here's my function again. Again, this is the same function, 1 minus x squared. It has a root at 1. I'm going to use 2 rectangles again, but I'm going to change how I calculate their height. So here, I divide the interval in equal pieces. So 0 to 1/2, 1/2 to 1. But now let's use a right-hand sum. So I'm going to calculate the height of each rectangle based on going up to the right-hand side now. And so what I will do is this. So this gives me my first area, A1. But now look at what happens to the second one. The second one, the height is calculated on the right endpoint, which gives me something with no height, right? So that means that A2 is equal to 0 in this case. But nonetheless, we're doing this for illustration. This is important for us to see. So let's keep talking about it for a moment. This tells me that my area is approximately equal to A1 plus A2. Now, we just said A2 is equal to 0. That's okay. Let's try and figure out what A1 should be. Well, in this case, A1 has the height given by the y value at 1/2. We already calculated this. This is 3/4. And so this tells us now that the area of A1 is height times base plus the area of A2 now, which we already said is going to be 0. So this gives me 3/8, which is significantly smaller than our previous estimation of 7/8. But let's take a look at something. I didn't overestimate the sum this time, right? Because A1 is entirely contained below my function. But what's missing now is tons of area. I didn't count that, and I did not count that. Okay, so clearly neither of these are very good, but what's the practical use of them? What was the point of me even doing this? Well, this gives me some bounds on my area, right? In the first case, I overestimated. So I know that my area is smaller than 7/8. In the second case, I underestimated. So that tells me my area is smaller or is bigger than 3/8. Not bad, right? Because this tells me something that I didn't start with. This tells me that my area has to lie between 3/8 and 7/8. That's an interval of with 1/2. That's a lot better than when I started, when the area could have been 0.01, or it could have been 10 to the 16, right? I've narrowed it down to a smaller interval. And I can repeat this process, right? I can do this over and over and over again. And so let me just show you what starts happening to the values. Okay, so this is, let's make a little chart here. The first column of this will be the number of subintervals. Okay, so what I mean by the number of subintervals, that's how many rectangles I'm going to be using. So we already saw this in the first case, we had 2. And the next one we will call the right sum. So the right sum, by that I mean using the right endpoint for the height of this area, or for this rectangle. I'm going to use the left sum, and that is going to be the first case that we use, where we use the height on the function to the left-hand side. And I'm going to present one more. I'm going to throw a curveball out. I'm going to call it the middle sum. Now, what do I mean by the middle sum? Well, there's smart people watching this, right? I imagine that most of us can figure this out. The first case used the right point of the, or the left point of the interval to find the height. The second case used the right point of the interval to find the height. Well, the third case, the middle sum, is going to use the middle of the interval to find the height. So we would come up from right here, and this would give us our height. Okay, so what did we already see? We saw that the right sum gives us 3/8. I'm going to write this in terms of decimals so that we can see a little bit of convergence going on here. So this is 0.375. The upper sum we already did, or sorry, the left sum, this was the overestimate, that's 0.875. Now, I'll spare you the gory details. What happens if you use the midpoint here? Well, this gives you 0.6875, so somewhere sort of in the middle. Okay, so then again, I'll spare you some gory details. Let me just show you what happens. What happens if I use the 4 subintervals using the right sum? So this is the lower estimate, right? This, by just from the picture that you can see above, this is still going to underestimate. This gives me 0.53125. My overestimate using my left sum is going to be 0.78125. So now we've narrowed that interval that this thing can belong to, right? This is an interval of 0.25. Originally, I had an interval of 0.5. So I took the interval that A can belong to, and I crushed it. I put it in half. And so what's the middle sum? Well, the middle sum gives us about 0.671875. Okay, so I don't want to get too boring for everybody here, but you can keep doing this, right? You could use 6 subintervals, or you could use 8 subintervals, or I don't know, 32. Why don't I just show you what happens as you use a lot more? So let's go all the way down to 1,000. Probably going to need a computer to do this. The computations are going to get cumbersome. So I would program this into a computer long before I'm going to do this by hand. So what's the lower estimate on this? Well, here we get 666,1665. Now, what's the overestimate? 0.6671665. Remember, the left sum is overestimating, the right sum is underestimating. Look what we closed the interval down to. we have the area under that curve up to 3 decimal places. The error here is 0.001. And let's see what the middle estimate gives us. 0.66716, sorry, 666 again, 6675. Okay, so it's right in the middle, but that's pretty darn good, right? We can over and we can underestimate these things, and we can see this convergence, this tightening of the bounds here to get us a very, very close approximation. Okay, so let's take a look at an application of where this actually comes from, where we can actually use these ideas. Well, one place where this comes from is from distance traveled. Okay, so imagine a car or something that moves is going down a straight path without changing direction. Okay, so it's just a straight line. We're going to keep things super simple for ourselves. Okay, so then at time t, I'm going to let v of t represent the velocity of this car. Now, if you've taken a calculus class before, you should remember something. First of all, if s of t is the position at time t, then s prime of t has to be the velocity, right? The derivative of this thing. So one thing you can do is you can calculate the position of this thing by simply finding an antiderivative for v. And so if you start at t equal to some initial point A, and you end at t equal to some terminal point B, well, the distance that you traveled this is clearly going to be where you ended versus where you started. And final position minus initial position. Okay, that's great, right? That's a little bit of calculus for us. We had to find an antiderivative. But let's put on our data scientist cap for a second. And imagine that, as you would expect in real life, a function like v of t is highly unlikely. Has anybody ever seen an actual function that tracks the motion of something for continuous time? No, right? So, okay, that means that s of t is probably inaccessible. So that's not going to help us, right? We're probably not going to be able to use this at all. So then how can we do this? How can we estimate the distance traveled if we're just collecting data? Well, what we can be doing is we can collect the velocity. We can measure the velocity, maybe using a radar gun at specific instants in time. So what you can do is you can think of time as being discretized. It starts at A, and you have a point where you measure the velocity, another point where you measure the velocity, another point where you measure the velocity, all the way up to some final point before you finish. Well, then what you're really doing is you have these discrete calculations of the velocity. You're checking at each one of these moments, what is the velocity? And we're going to assume that these things are taken at equal intervals, delta t. So the question is, how can you estimate the distance that you traveled? Well, if you think back to what's happening here, to calculate an antiderivative, we need to calculate an integral, an indefinite integral. And now that we've discretized this, we can use that same notion that we had on the previous page. We can think of these things as rectangles, And we can say that the distance traveled is approximately the area of the first rectangle. It has height, the velocity measured at time 1, times the base, delta t, the length of time between each time step where you measure, plus the height of the next rectangle, v of time 2, times the base of that thing, plus, and you can keep adding up all of these rectangles to give yourself a nice approximation of the distance that this thing has actually traveled. And of course, just like with the previous analysis that you saw, the more time points that you collect, so the smaller delta t is, the better the approximation that you are going to make of this distance that you traveled. Okay, so one more example of where I might actually need to use something like this. Oh, and this would come from finding the average value of a function. We're probably pretty good at calculating averages, right? Because that's how a lot of grades are calculated. So we know how to calculate averages pretty well when you're given a finite collection of objects. But what if I make life a little more miserable for us and I say, I give you this function, y is equal to f of x on, again, some interval a to b, and I say, what is the average value of f of x over this interval? Okay, so, why would you need to do this? What's a place where you need to do this? Well, you could go back to the previous example. You can ask, what was the average speed? What was the average velocity that someone was traveling at while this was happening? Or let me give you another example. Imagine you've got a big tank. Oh, that's not great. You've got a big tank, and there's water in it, and it's sloshing around. But you're smart, and you put up maybe a little yardstick right here on the side. And again, we're going to think of this as a continuous valued function. So at each time instant, for example, that's what your independent variable x could represent, just like in the previous example. You measure the height of that water that's sloshing around just on the side here, right? So then f is going to measure the height along the yardstick. So you want to calculate, what is the actual height of the water in here when it's not sloshing around? In this case, you're going to arrive at an average, right? You want to find the average of this function over the measurements that you made. And again, I'm going to think of it as a continuous valued function, but you can do the same thing we did for the velocity, and you can discretize this, and you can put on your data scientist hat, and you can be, a true sort of scientist doing these kinds of experiments. So the question is, what happens? How do we calculate the average of these things? Well, you're going to do exactly the same thing. You're going to discretize up the interval. Into delta x components, right? So that's going to be the same as my delta t on the previous piece here. And you are going to calculate this sum, these discrete rectangular sums over this entire discretized space a to b, and then you're going to divide by the length of that interval. Right? This is just like a weighted average that you would have with a discrete collection of variables. Imagine I calculate your grade for this class, and there's 5 items submitted, and the first one is worth double what the second one is worth. right? So the way that we calculate that out is we take the weight and we multiply it by the value that you got on that first assignment, plus the weight of the second assignment times the value you got on that, and so on and so forth. And you divide all of that by the sum of all of the weights. Now, you typically don't see this dividing by the sum of all the weights because we usually make this sum add up to 1. So you would never really see it because you're just dividing by 1. In this case, the same idea, the sort of weight of this interval, the total length of the interval is b minus a, right? This thing has length b minus a. So you can think of that as being the continuous version of the weights of all of these averages. Okay, so let's formalize a lot of what we were just talking about. And this is the idea of a Riemann sum. So let's push it into a little bit of the abstract realm. And let's say that I just give you a completely general function. Doesn't matter what it is. I want you to calculate the area underneath the curve between two given values, right? So I have this area right under here, and I say, what is that? Okay, well, let's think of what we just did. We just said that you can approximate this using all of these rectangles. And so then what we can ask ourselves is, how do we take this into the completely abstract realm? So let's first define a spatial step size. So I'm going to say delta x is equal to a spatial step size. This is going to be the length of my little intervals down here that are the widths of my each of my rectangles. And I'm going to keep it simple, right? I don't want delta x to be some ridiculously complex thing that I have to compute all the time. I'm going to say delta x is going to be b minus a, the length of the interval, divided into n different subintervals. So in this case, this n is equal to the number of subintervals. Think back to what we did with 1 minus x squared, right? What happened there? When I had two subintervals, well, b was only 1, a was 0. 1 minus 0 divided by 2, 1/2. That was the length of my subintervals. If I used 4 subintervals, then I would have 1 minus 0 divided by 4, 1/4, right? So this is how we're going to do this. We're going to stretch, and we are going to divide this entire interval into exactly n subintervals. And that means that we are going to define each of the points on these subintervals, or the endpoints of this. We'll say x0 is equal to a. That's where we start on the left-hand side. And then x1 is equal to a plus the length of the first subinterval, right? We're moving forward to the right. So this is b minus a over n. And then the next one is going to be x2, which is equal to x1 plus the length of the next subinterval, which we can rewrite it as, since we know what x1 is, this is a plus 2 b minus a over n. And so in general, we can say that x sub k, the kth point in here, is equal to, a plus k steps or k intervals forward times the length of each one of those intervals. If you wanted to use different delta x's for each interval, for each little subinterval, you want some to be big and some to be small, that's fine, but it's really going to make this term at the end of your x sub k's very ugly, right? The only reason I could multiply k in there is because each subinterval has the same length. And so then the subintervals, they become xk to xk plus 1. And so then, now that we have the base of each of these rectangles, we have to ask ourselves, what will be the height? And again, if we want to keep this completely general, then we can pick any point inside this interval, and we can use that to define the height. So height of rectangles. We're going to pick some number, ck, between, between xk and xk plus 1, something in the interval. And so the height equals f of ck. Now, let me give you an example. If ck is equal to xk, then I get my left rule that I talked about. And if ck is equal to xk plus 1, then I get my right rule. Or I could have my mid rule, where ck is equal to the halfway point between these two. So I add them up and I divide by 2. There are lots of ways you can do this. Just like with the delta x, you can choose a different method for finding the ck's for every single subinterval. It's completely up to you, but I would recommend not making your life miserable in this case.
Okay, so let's conclude this section with a simple example. Let's go back to where we started, and let's ask ourselves to find the area below y is equal to 1 minus x squared on 0 to 1 using Riemann sums. Okay, so how are we going to do this? Well, we're going to use that same idea where we have these finite number of rectangles. And so let's set it up first. Well, in this case, first, a is equal to 0 and b is equal to 1. And so that means that we're going to subdivide our interval from 0 to 1 into n different intervals, and each one is going to have length b minus a over n. So b is 1, a is 0, 1 over n. So that means that the points we're interested along this are 1 over n, 2 over n, 3 over n, 4 over n, all the way up to n minus 1 over n. And finally, we can think of 1 as n over n. Now, we're going to calculate this Riemann sum using the right rectangle rule. So, So use the right rule. So that the height will be equal to f at k over n. right? So the k comes from the kth subinterval, right? You can see that the right endpoint of each interval is given by 1 over n, 2 over n, 3 over n. So in this case, k is going to count from 1 all the way up to n, where your final endpoint is given at 1. Okay, then let's set up this Riemann sum. You're going to count over the n subintervals. So that means that we use the sum notation. K is equal to 1 to n of f of k over n, the height or the length of each rectangle, multiplied by the base or the width of each rectangle, which in our case is b minus a over n, so 1 over n. And we know what our function f is. It's 1 minus x squared. So f evaluated at k over n is 1 minus k squared over n squared multiplied by 1 over n. Okay, so don't get intimidated by this sum. This sum is over k. N, it will be fixed for the time being, right? So what we're doing is we're summing up over values of k equal to 1, k equal to 2, k equal to 3, and so on and so forth, right? Just representing the first subinterval, the second subinterval, the third subinterval, and so on. N is the number of rectangles that are present in here. So in this case, n can be thought of as a constant. It's k that's being considered in the sums. So let's multiply this out and let's distribute the sum over each of these terms. So first we have the multiplying out. So 1 over n minus k squared over n cubed. And let's distribute that sum over each one of these terms here. So I'm going to take the sum of this piece and the sum of that piece, and I'm going to subtract them, right? This is a nice distribution property of all these sums. And so this gives me k equal to 1 to n, the sum of 1 over n minus the sum from k equal to 1 to n of k squared over n cubed. Now, let's look at that first sum first, right? 1 over n is a constant. It's not changing for each term in the sum. K is what's changing. So again, be careful. I know there's a little bit of abstraction here, but you're essentially adding up 1 over n exactly n times. You're doing it for each value of k. So the sum here is going to be 1 over n times the number of times you added it, which is n. And similarly, since 1 over n is a constant, let's pull it out from the second sum. And now we have the sum of the square numbers running from 1 to n. Luckily, we have a formula that'll simplify this for us, right? There's a nice compact formula that tells us what the sum of the first n integers is. But before we get there, let's clean this up a little bit. 1 over n times n, that's 1. That's great, right? That is nice. Now, what happens over here? Well, we get 1 over n cubed, and then times the sum of the first n squares, which I will give you the formula. It's n times n plus 1 times 2n plus 1 divided by 6. And I'm just going to multiply in the 1 over n cubed. I'm not going to simplify anything just yet. We'll just talk about what this says. Okay, so what does this actually tell us, right? This gives us a nice compact formula. This tells you that if you want to take n rectangles, you can skip from right here all the way down to right here to tell me what that sum is going to be if you're going to use the right rule. This is very nice, right? Because I could use n equal to 2, just like I started with. But I can also use n equal to 10, which is sort of becoming a pain when it comes to computations, right? That's 10 areas I've got to add up. or I could use n equal to 100, or even n equal to 1,000, right? Remember, I started this lecture by saying it gets a lot harder, or it just gets a little bit more annoying as you have more and more rectangles, because it's just more computations to do, more multiplications, whatnot. But in this case, give me a value of n. I'll put it into this formula, and I'll tell you what the approximation of the sum is. Now, let's finish this off, right? The question didn't say, what is the approximate area under the curve? It says, what is the exact area? Well, what we'll make formal in the next lecture is that as the number of rectangles goes to infinity, you converge the area under that curve. So let's drift into the realm of calculus again, and let's take a limit as the number of rectangles goes to infinity. What I'm going to do, instead of, I'm going to expand that numerator of this function out, make it look a little prettier, just to simplify our lives a little bit. Here we go. Okay, now let's distribute that denominator over all of the terms so that we can take this limit. So in this case, I get, sorry, this is a cube down here. So I get 1/3, and then I get minus 1/2n, and then I get minus 1/6n squared. Now, I'm asking myself, what happens as n goes to infinity, as I take the number of rectangles to infinity? Well, 1 is constant, that doesn't change with n. 1/3 is constant, that doesn't change with n. 1/2n, as n gets big, 1/2n gets super small, and this goes to 0. Similarly, as n gets really big, 1/6n squared gets super small and also goes to 0. And this tells me, I'll try and squeeze it in at the bottom here, that the limit here is equal to 2/3, 0.6 repeated. Okay, this is good, right? Think back to where we started at the very, very beginning. Let me scroll back here. Look what happened with 1,000 subintervals. We got 0.66 for the 666, sorry, for the right sum, and the left sum is 0.667. Remember, we said this is a nice, small, compact region where we're over and underestimating. And look at how close that is. We said it's within it's up to 10 to the minus 3 close to each other. And we can see that this is very, very close to converging, at least up to some tolerance, based on what our theoretical and our exact answer is. It should be 2/3. So taking 1,000 rectangles is not a bad thing in this case, right? We can see that we got a very nice approximation and that we got this nice convergence based on these Riemann sums. Okay, so we're going to come back to this in the next lecture. So thank you very much for joining.